Welcome back to another project video. Thanks in advance to those subscribing and commenting. This multi-part video series chronicles how I built a data logger to keep tabs on our domestic utility water supply. An important indicator is how well the main line pressure is maintained. Water mains need to overcome uphill runs and stay ahead of demand increases from residential growth and irrigation. Pumping stations need to provide adequate capacity. Our neighborhood is located in a rural, semi-arid area of southwest Colorado, which includes canyons, valleys, and grade changes. Supplying water to customers here presents its challenges. Some remote homes haul their own water. Our house is at 7,000 feet elevation and has a utility water main connection. Tri-County Water installed and maintains our water distribution system. Over the past 8 years, our water supply has been good. Local reservoir levels also have been good. Snowpacks from the San Juan Mountains feed the reservoirs. If water problems are looming, it won't be for lack of water. It will come from demands exceeding the water supply system capacity. For those living in the Pacific Southwest, I encourage them to conserve water. This video is part 1 and covers how water arrives at our house, static and dynamic pressure readings, the Ashcroft pressure sensor, and showing the pressure readings. Let's dive in. Here's a simplified diagram of our water system. We'll start with the tank up on the hill. This feeds a main that runs in the road. The road is graded uphill, which causes a loss of pressure. A pumping station increases the pressure, which feeds another main in the road. This continues uphill and passes our house. Just at the edge of our property, we have a city water tap, which includes a meter. From there, a plastic pipe runs 60 inches underground below the frost line and comes into the crawl space under the house. Pressure is regulated down to 45 psi and feeds all our domestic water needs. Let's zoom in on some photos of the physical parts in the system. The storage tank sits up on the hill and water is pumped into it from an external source. The height of the tank creates hydrostatic pressure, which feeds houses along the road on the way up to the pumping station. Although somewhat flattened in the photo, the road climbs steadily. Pressure is lost but restored via the pumping station. The road from the pumping station to our house is also an uphill grade. Near the top of that grade is our city water tap. All right, we're leaving our driveway. I walk up the road here, locate our Tri-County water tap. So we'll pivot here and head east. And this is it right here. This is our Tri-County water tap. This is actually on the edge of our property. And you'll see this cover here. That goes down 60 inches. And then there's a plastic pipe that runs all along our property and then eventually ends up in the crawl space in the house. So that's kind of how we get water. As mentioned, we got a plastic pipe that runs from the Tri-County water tap in the road, ends up underneath the house. So what we're going to do is we're going to crawl into this crawl space and find out where the plastic pipe comes in from the street, and then we'll take a look at the PRV, pressure regulator valve, and where the Ashcroft pressure sensor is installed. So let me get down under there. I gotta get my headlamp on and we'll see what we get into. Okay, we're in the crawl space. This is our main air duct, and actually off in the distance there you can see maybe where the city water line comes in. So I'm kind of skidding along here. There's not a lot of space down here, so I got to get underneath the air register here, and then we'll get on the other side and we can see what's going on there. Okay, there's where the city water line comes out, right there. Probably see that. Runs up along here, and so we'll slide over a little bit, and right there is our shut-off valve, which shuts the water off at the street. And then right there, that's the Ashcroft pressure sensor on the city water side. And then we move right there is the Watts pressure regulator. We're actually running 45 psi in the house. And then this here is what feeds all the water in the house, PEX tubing. But let's see if we can get right there. That's the Ashcroft sensor, and then this wire runs up into the house, and that's what's going to go into my data logger. So that's what's in the bottom of the house here, in the crawl space. That's how it works. Let's talk a bit about static and dynamic pressure readings shown in the graphic. Simply stated, static pressure will be the reading when no water is flowing. At the bottom, pressure readings taken at points A and B will be equal. This means we can get a water main pressure from inside the house. When a faucet is opened or some other water demand is called for, the pressure at point B will be less than the pressure at point A. The reason is pressure drop in the piping. Pressure drops will increase with longer piping runs, smaller diameter piping, or increased demand. Our buried water line is 1 inch in diameter and approximately 200 feet long. For normal domestic demands, this is adequate. If the washer, dishwasher, both sink faucets, shower, and someone washing the car were all demanding water, I guess we'd see a problem. This, however, isn't normal usage. Over several days, we've seen the dynamic pressure drop to 73 psi. The house regulator is set to 45 psi, which provides an adequate margin. At this point in the project, I don't know when or why we dropped to 73 psi. If this is a worst-case low pressure, it remains 28 psi above the regulator. More analysis is required. The Ashcroft G2 series sensor I used is intended for industrial applications. It accepts a power range from 9 to 36 volts and outputs a 1 to 5 volt signal. This means 1 volt is 0 psi gauge pressure and 5 volts is 200 psi. It's easily read via a 0 to 5 volt analog input like the Arduino Nano V3 PCB offers. The linear mapping function is expressed as psi equals the quantity V minus 1 divided by 4 times 200. I used a rolling average consisting of 10 readings taken at 100 millisecond intervals for my final pressure reading. This stabilizes the final reading. The sensor is accurate and responsive, and I'm happy with this product. I've included a full view of the G2 series with a DIN-C connector for reference. The DIN-C connector has screw terminals and a strain relief for wiring. Okay, we're up in the living space. Got this little slide cover here. Probably see that. And this actually is where the shutoff valve is for the water in the house. But the wire from the Ashcroft sensor, I was able to feed it up, sneak it by one of the pipes in the hole that was drilled in the floor. So that's coming up, and what I did was I just set this up on the kitchen table. This is my Nano V3 interface board. I'll do a video on that board, which will be informative for those people that are interested in it. But the software is on that, and the analog to digital conversion is on there as well. So that's what's reading the sensor. So we got a 12 volt power supply. This is a bit overkill. The system draws 100 milliamps at 12 volts. This is a power supply I just had kicking around, so I used it. So that's what feeds the DC power into the system. And here's the input module that's got the LCD mounted in it, and it's got this input rotary encoder, which is a dial that spins, and then there's a push to select. I'll do a video on this enclosure as well, how I made this. It came out pretty well. So that's the whole system. It's been testing here on the kitchen table just to make sure the sensor's reading and just to make sure everything is working properly. So, okay, here's our LCD and input box. Home screen is displayed. We've got 4 menu items. The little dial here moves the arrow. We can pick a menu item. I'll just go through this pretty quickly. This is where we can change the intensity of the backlight, so we'll just drop it down. You can see that. We'll put it back up here to 8, which is the maximum. So here's our pressure reading, and we're in 107 pounds and change, and that's what we're measuring off the street. There's no water flowing in the house right now, so this is going to be a static pressure reading. So I'm going to go over and open up a faucet, and we should see this pressure drop a little bit. So it's keeping up with the demand pretty well. It's dropping down a little bit, but it's not too bad. So you can see how that works. So this would be considered a dynamic pressure. Let me close the faucet. That pressure will pop back up. So that's kind of how that works. And I can get out of this. And I've got a min-max reading here, which simply takes the pressure and compares it to a previous reading, and if it's less than, it updates the min, and if it's greater than, it updates the max. So this is what we've seen for the elapsed time period. So I've got that set over here, and I've been testing this. It's actually been running 43 hours and change, so that's kind of the test period. I set it up a couple days ago and just let it run just to make sure that everything was working well. So we can go back here and look at this min-max again. So that's over a 43-hour period. And again, that low pressure reading, we had the washer running and we had some other things running and showers and whatnot. So it's understandable that we're going to see quite a differential in those two pressures. But the regulator is set to 45 psi, so even at 73, we're still ahead of where the regulator needs to be satisfied. So it's all good. Let's go back here to the pressure. That little bit of movement in the tenths and the hundredths position is probably noise and or digit bobble. I wouldn't pay too much attention to that, but the pressure in the units position where you see a 7 there, that's probably significant, and the pressure does vary out in the street as people open up their faucets and close their faucets and do things on the water line. So that's kind of interesting, but generally we're running around 107, 110 psi is generally what we're getting here. And when the plumber was here, we verified that with a manual gauge, and he was getting actually 110 the day he was here. So I think everything is pretty good. So that's how the pressure readings are taken, and that's how we're going to monitor this. The next part of this is feeding this data into a data logger. I got to write some software for that so I can timestamp these readings, and then we can build up a file where there's a pressure reading, a date, and a time, and each reading can just be added to the file. I haven't figured out yet whether I need to take readings every second, every 10 seconds. I'm not sure yet what to do about that. But with that file building up, then we can go ahead and import that. It'll be a CSV file. We can import that into a spreadsheet tool. We can do a nice graph. So that's a project that is not done yet. It will be, and I'll get a video out on how I did that and show all the details on that. So that's the story on the pressure readings. Let's wind up with a few summary points. Utility main pressure can be read from the house. The G2 series Ashcroft sensor works well. Static pressure is an indicator of how well the main can meet demand. The goal is to keep track of our water supply. Collected data will help promote awareness in our county. Links can be found in the description for more information. Per usual, please leave comments to share your thoughts. More project videos forthcoming.